Today, we are pulling back the curtain on one of the most critical jobs your computer's operating system is doing every single second of every day, simply deciding what to do next. This is the art and science of CPU scheduling.
Have you ever really stopped to think about how you can be listening to music, browsing a dozen tabs on the web, and have all those other apps running in the background, all at what feels like the exact same time? It really does feel like magic, but it's not. It's actually a very, very clever juggling act performed by your computer's central processing unit, or CPU.
Okay, to really wrap our heads around this, let's use an analogy that we'll stick with. I want you to imagine your CPU is a single, incredibly fast barista at a super busy coffee shop. And all those programs you're running, well, they're just customers in a long line, and each one has a different, unique coffee order. The scheduler, then, is the manager who's telling that barista who to serve next. So, let's get just a little technical for a second. What this all means is that CPU scheduling is simply the method the OS uses to pick the next process from the ready line and give it to the CPU to execute. And the goals are actually pretty simple. You want to keep the barista, the CPU, busy, you want to get everyone their coffee quickly, and you want to make sure the whole system feels fair to all the customers waiting.
All right, so when you get right down to it, every single scheduling strategy has to answer one big question. Once our barista starts making a drink, can they be interrupted to do something else? This one simple question splits all scheduling algorithms into two major families. First up, you've got what's called non-preemptive scheduling. And in our coffee shop, this is super simple. Once the barista starts making that complex multi-step caramel macchiato, they finish it, period. They will not stop, even if the very next person in line just wants a quick shot of espresso. The current job runs until it's totally done.
And then there's the other side of the coin, preemptive scheduling. Here, our barista can be interrupted. They might be halfway through that complicated latte when a new high-priority customer comes in needing a quick espresso. The barista can actually pause the latte, pour that espresso, and then come right back to the first order. And this, by the way, is how modern systems like Windows and macOS actually work.
And this really gets to the heart of the trade-off, doesn't it? Non-preemptive is simple. It has very low overhead. But a single long process can hold up the entire system. Preemptive, on the other hand, feels way more responsive and fair, but all of that stopping and starting, what we call context switching, adds its own layer of complexity and, well, its own overhead.
Okay, let's dive into some specific algorithms. And we're going to start with the most straightforward one you can possibly imagine, the one that works exactly like standing in line at the grocery store. It's called first come, first served, or FCFS.
So, let's set the scene. 3 customers, or processes, right? They all walk into our coffee shop at the exact same moment. P1 has an order that's going to take 5 minutes to make. P2 has a super quick 3-minute order. And P3, well, P3 has a big, complicated order that's going to take a full 8 minutes. Now, with first come, first served, the approach is pretty blunt. The barista just takes them in the order they're numbered. P1 goes first, then P2, then P3. But wait a minute, you see the problem here, right? Poor P2 with that super quick 3-minute order is just stuck there waiting for P1's entire 5-minute order to finish. That is not very efficient.
And this exact situation, it actually has a name. It's called the Convoy effect. It's the perfect name, right? It's literally like being on a single-lane highway stuck behind one giant slow-moving truck. You've got all these little sports cars, the quick jobs, piling up behind it, and the whole flow of traffic just grinds to a halt.
And we can actually put a number on this pain. For this little scenario, the average time each process just sits around waiting is 4.33 milliseconds. So, here's the deal with FCFS. Yeah, it's simple and you could argue it's fair, but man, it is definitely not fast.
So you gotta ask, how do we bust up this convoy? Well, what if our barista was just a little bit smarter? And that brings us to our next approach, shortest job first, or SJF for short. Okay, same 3 customers, same orders, but this time with SJF, our barista takes a quick look at all the order tickets and says, aha, P2, your order only takes 3 minutes, you're up first. After P2 is done, they grab the next shortest, which is P1, and only then, at the very end, do they tackle the big 8-minute order from P3. And just by making that one simple change, just by reordering the jobs, look what happens. The average waiting time plummets from 4.33 all the way down to 3.67 milliseconds. That's a huge improvement. We literally made the entire system more efficient just by being a little strategic.
I mean, just look at that side by side. The difference is crystal clear. We've shaved off a ton of wasted waiting time. And here's the really cool part. SJF is actually provably the best possible algorithm if your only goal is to make the average waiting time as low as possible. It's mathematically optimal.
So, what happens if we take this idea and we combine it with that preemptive thing we talked about earlier? Well, you get something called shortest remaining time first. And this is where it gets really dynamic. Imagine our barista is working on that 5-minute order, and 2 minutes in, a new customer walks in with a super fast 1-minute order. The barista can actually pause the first order, knock out the new 1-minute job, and then go back to finish the original one. Talk about responsive.
Okay, so far we've only been talking about how long a job takes, but what if some jobs are just more important than others? This brings a whole new layer to the game, what you could call the VIP pass. We call it priority scheduling.
I mean, think about it. On your own computer, right? You moving your mouse cursor smoothly across the screen is probably way more important in that exact moment than some big file that's downloading in the background. The operating system has to have a way of saying, hey, you're critical. You get to cut the line. It's not about being the shortest, it's about being the most essential.
And the rule here is brutally simple. Every single process gets a priority number. The scheduler just looks at the line and gives the CPU to whoever has the highest number. That's it. The VIP customer always goes next, no matter how long their order is or who is waiting before them.
But you can probably see the huge glaring problem with this, right? It creates a really dangerous risk called starvation. Imagine our coffee shop. What if there's just a constant, never-ending stream of VIPs coming through the door? Those regular low-priority customers, they could literally wait forever, never getting their coffee. And on a computer, that means a low-priority process might never get its chance to run. Ever.
So, as we're starting to see, each of these methods has its own superpower and its own kryptonite. And that really brings us to the fundamental truth of all this. When it comes to CPU scheduling, there's no magic bullet. There is no one single perfect answer. So let's just recap, right? What's the bottom line? It's all about trade-offs. FCFS is dead simple, but it gives you those awful traffic jams, the Convoy effect. SJF is amazingly fast on average, but it can totally ignore the big long jobs. And priority scheduling? It's perfect for critical tasks, but it carries that huge scary risk of starvation. This is why most modern schedulers actually use a clever mix of these ideas to try and get the best of all worlds.